Okay, so today we're going to take a look at open sentences and two variables. The major objectives here are to find solutions to open sentences that involve two variables as ordered pairs, and then make sense of the ordered pair solutions when we're looking at word problems. An open sentence is defined as something that has two different variables and is said to have a solution that is a pair of numbers. And you know this as a coordinate. Since we have two variables in the open sentence, then there are two values that are needed. So for example, if we had something like 2q plus 3m equals 7. That's a simple example here, and we can see that clearly we can't figure out what m and q are because there's two variables. But if we give some value for m, say m is 2, then it makes this part become 6, and now we can find out what q is. So if we wrote our ordered pairs as m comma q, we could say that when m is equal to 2, we could always figure out what q is. And then when m is equal to 3, we could figure out what q is. And when m is equal to 4, we could figure out what q is. And we get a family of values here. And we'll see that those are the possible answers, and those are the pairs of numbers. Notice these are all in pairs. Let's take a look at our first example. Find 5 different solutions of 4x plus 3y equal 24. Now, there are many solutions to this. Technically, there are infinite solutions to this. But we are going to simply look at 5 different ones. And to make it easy on us, we'll pick numbers that are simple. But first, we're going to notice that we have an open sentence written in the form of ax plus by equals c. It may be useful to solve this for y first. So let's go ahead and do that. Now, you might say, why would I solve for the variable y here? Well, we'll show you in a minute. If we move the 4x over and we have 3y equals 24 minus 4x, and then divide by 3, we get y equals 24 minus 4x all over 3. Now, what you're going to notice here is that we've solved for y generically, so we have the solution for y. And we can sit here and just plug in values for x and get our y values and come up with 5 points. Remember, we want to get 5 different data points here. So if I pick values for x, we can figure out all the values for y. So to make it easy on yourself, it usually helps to use 0 for x, and then like 1 and -1, 2 and -2, and work your way around there. But you could pick any number. So for the sake of picking any numbers, I would choose -3, -1, let's try 0, 1, and let's try 4. Because I'm going to avoid symmetry just to show you that it doesn't matter what numbers you try. Now, all you need to do is go ahead and plug this number in. So we start by taking the -3 for x, plug it in right here, and then come up with whatever y is, and that goes in, right up here. Then take the -1, plug it in for x, figure out what y is, and that answer goes right here. So the first one, we plug a -3 in, we're going to have minus, this is 4 times -3, and I'll go through the first one with you. Okay, just like that. We plug in the -3 from here, right into the x, to give you the y value. Well, this is going to be 24 minus -12, or 24 plus 12, that's just 36. 36 divided by 3 happens to actually be 12. So the coordinate here is -3, 12. And what I've done for the other 4 here is just filled in the values you get for y when you plug in their corresponding x coordinates. It's pretty much the same thing as making an organized table of data. So whenever you have an open sentence, you can use a table function as well, but the problem is, or the thing is to remember that if you're going to use your calculator, it has to be in this form right here, y equals. And you would have to plug this into y1, and then take a look at your table. Looking at your x coordinates, you could find your corresponding y coordinates. So we have 5 points here. Now, if we graph these points, we'd see what we'd have, but we're going to hold off on that just for now. So these are 5 possible solutions. Again, there are an infinite amount of solutions to this open sentence. Example 2, solve the equation 3y minus 4 equals 3x if the domain of x is given as the following. So we're given the values that x can take on. Remember, the domain are the possible values for x. So here, if we want to know what the values of x that can be taken on here, we can simply plug them into this equation and try it. But again, to make it easier, let's go ahead and solve for y. So I'm going to go ahead and add the 4 over. Add that 4 over here first. Then I'm going to divide by 3, giving us 3x plus 4 all over 3. So that's the generic solution for y, 3x plus 4 all over 3. Now, we're told the values of x this time. We are told them. So let's just go ahead and make a little chart to make it easier. I'm going to told x is negative 2, 1, 5, and 7. So let's plug in those x values. When we plug in the negative 2, we're going to get approximately negative 0.7 over here. Okay, what am I doing again? I'm taking this negative 2 right here, plugging that in for x. This becomes negative 6, plus 4 is negative 2. Negative 2 over 3 is negative 2/3. Negative 2/3 as a decimal is negative 0.66666 repeating, which we can round to negative 0.7. Okay, that's my first value. Plugging in a positive 1 in here for x, we're going to get 2.3 over here for the y value. Plugging in a positive 5, we're going to get 6.3, and finally plugging in a positive 7, we're going to get 8.3. So these are like my 4 coordinates, okay? So if we wanted to solve the equation, if the domain is given as the following, this would be the solution, really. Negative 2, comma, negative 0.7, 1, comma, 2.3, 5, comma, 6.3, and 7, comma, 8.3. And a lot of you are probably noticing already that there's some sort of patterns that happen to occur here. Okay, so keep those in the back of your mind as you go through these problems. Example 3, we take a look at a word problem now. It says Paul has $22, and he buys notebooks costing $2 each and a binder costing $5. If he spends all $22, how many of each does he end up buying? Well, here the issue is that the notebook must cost $2 and the binder must cost $5. So we need to think about all possible scenarios. So let's start by saying that, for example here, X is the number of notebooks purchased, and Y is the number of binders. So again, X are $2 each. So $2 times the number of notebooks plus $5 per binder times the number of binders has to give us a total of $22. He spends all his money, so it equals 22. If there was change, the problem would be different. Now, we can then say to ourselves, well, there's many possible answers that can go in here for X and Y, but the key is to remember that you can't buy a fraction of a notebook or a fraction of a binder. So we need to find all the possible X and Y values that are whole numbers that make this equation true. So we go ahead and we take a look by listing all of our possible values. Well, let's start. Let's do this like we did last time. Solve for Y first. So move the 2x over. That'll give us 5y equals 22 minus 2x. We divide by 5. Y is 22 minus 2x all over 5. Let's take a look and think about this for a moment. You cannot buy negative amounts of things. So we know that right away that our x values must be greater than or equal to 0, and our y values must be greater than or equal to 0. We can't have negative numbers. We also know that x and y have to be whole numbers. Okay, so this is an example of where we're looking at the whole number set. Okay, we start with 0, and it can be any number greater than that, but they must all be whole numbers. So let's take a look and make a table of values to see what's going on here. So that's our equation still. So let's say we have x values and the y values. I'll make the table in the other direction this time. It doesn't really matter. Okay. And let's say that this person buys 0 notebooks. So x is 0 for the sake of this. Well, if he buys 0 notebooks, if I go 0 in for x, we're going to end up getting 22. And I'll follow here. 22 minus 2 times 0, because the 0 goes in up here. So 22 minus 0 is 22. 22 divided by 5 is going to give us 4 and change. So it's going to be some decimal amount of binders. But we can't have a decimal amount of binders, so this is not going to be one of our solutions. So what I'm doing, if you notice, is I'm plugging in the x values, but I'm noticing right away that certain numbers give decimal answers. And those decimal answers have no significance on this problem. Well, let's try 1 here. So let's say we bought 1 notebook. Well, this becomes then, the 1 ends up going in right here now. So we get 22 minus 2. Well, that's just 20. And 20 over 5 is 4. So this one turns out to work pretty well right here, because we get whole numbers for each of these. So this means that if you bought 1 notebook and 4 binders, it would cost $22. Well, that's true. Binders are $5 each, notebook is $2, that's 20 plus 2 is $22 for the purchase. So you have to get a whole number is the idea. If we tried 2, we're going to get another decimal. 3 is another decimal, all the way up until we get to 6. When we get to 6, we get a whole number here. We plug in a 6 up here, we're going to get 22 minus 12, which is 10. 10 divided by 5 is 2. So here's our next answer. 6 comma 2. Well, let's see if this works. This tells me that we're getting 6 notebooks and 2 binders. Well, notebooks are $2 each, so this portion gives me $12 worth. And these are $5 each, so that's 10. $12 plus $10 is, again, $22. So this is one of our answers. Well, notice 7, 8, 9, and 10 all give decimals. The last possible solution is 11 comma 0, and that works also. You could buy 11 notebooks for $22 and buy no binders. So how many possible scenarios are there? There are 3 possible scenarios. Again, it could be a notebook and 4 binders from this portion right here. It could be 6 notebooks and 2 binders, or it could be 11 notebooks and 0 binders. Example 4. Find all positive 2-digit odd numbers. So odd numbers right away. 2-digit and they're positive. Those are restrictions. With the following property. When the digits are interchanged, the result exceeds the original number by more than 36. So what does that even mean? Let's take a look. So like say I pick a number like 21. Any random number. If I switch those digits, I get 12. Is the difference between these, or does the result exceed the original? No, it clearly doesn't exceed it. It needs to exceed it by more than 36. So this would not be an example that would work. But we can't sit here all day and try things, so we have to come up with some sort of an algorithm to help us with this part. So in order to do that, what we can do is start with our let statements. If you remember, a number like 21, it really means there's 2 10 holders and there's 1 1 holder. That's what this means here. A number like 48 means that there are 4 10 holders and there are 8 1 holders. So that's 40 and that's 8 really. So this value here is worth 1. There's 8 of them, but it's worth 1 each. This place is worth 10. This place is worth 10. So that means that this digit is worth 10 always, and this digit is always worth 1. Okay, let's keep that in mind. That's why it's called the tens digit and the units digit. Alright, so let's write our let statement now. Our let statement can say the following. Let's call the number u, comma t, or ut. So let's say let u equal the units digit. And let t equal the tens digit. So, right now, our number would be tu. Again, t represents the tens digit, and u represents the units digit. Now, with that statement, we could then say, and take a look at our problem, it says when the digits are interchanged, so when it's changed to become ut, like that, it says the result exceeds the original by more than 36. So the result is bigger than the original, or exceeds the original by more than 36. So let's take a look and make an equation of this. Well, right now in the original setup, this is worth 10 and this is worth 1. But now u is worth 10 and t is worth 1 in the new one. So on the left-hand side of the equation, again, we know that this is worth, t is worth 10, and the units digits are worth 1. And now that we switched it, this result should exceed the original by about 36, by more than 36. So if we take the original and add 36 to it, this will still exceed it. So we have now 10u plus 1t. Let me go through this one more time real quickly. The original is whatever is in this place and whatever is in this place. The next part is when you switch them. So because the t was worth 10 points earlier, now the t is only worth 1 point. Because the units digit is worth 1 point originally, now the units digit, which goes here, is worth 10 points. But we know that the result of switching, right here, the result, is greater than or exceeds the original by how much? By 36. Okay, by 36. So for a problem like this, we can see that we have an open sentence, but it happens to be an open sentence that's an inequality. So let's take a look and start combining some like terms. I'll move the t over, giving me 9t over here. I move this t over here by subtracting. I'll move this 1u over by subtracting it. That'll give me a 9u over here, and then it's a plus 36 still. Everything is divisible by 9, as we can see. So let's divide everything by 9. Makes our equation a lot easier for us. We're left with t plus 4 less than u, or u must be greater than t plus 4. u must be bigger than t plus 4. Alright, so let's take a look at what the heck this means now. The units digit must be the same as the tens digit, but it has to be bigger than that by 4. By 4. Okay, so in the tens digit, let's start, for example, and then the units digit. Let's say that the tens digit is 1. If the tens digit is 1, that means the units digit has to be greater than 5. Again, let's take a look at why this makes sense. If the tens digit is a 1, then the units digit has to be greater than, the same as the tens digit plus 4. So the units digit has to be greater than 5. Well, what numbers are bigger than 5? Numbers are 6, 7, 8, 9, and then can we put 10? We have to talk about that for a moment. But again, any numbers, 6, 7, 8, 9. But since this is in the units digit, we want odd numbers, because the beginning of the problem said, find all positive 2-digit odd numbers. So that means that u could really be either 7 or 9. So we could start with something like 1, 7 or 1, 9. Where does the 1 come from again? The 1 is the t value. T goes here, and then the u goes there. Okay, so that's my first possible solution. Next, tens digit if it's 2. Add 4 to that, gives me 6. What numbers are greater than 6? Well, again, 7 and 9. So this could be 2, 7, or this could be 2, 9. Next, we take a look at the number 3. If you add 4 to that, you're going to get 7. Well, what odd number is bigger than 7? Only the number 9 right now. Okay, only the number 9. And remember, this is the units digit, so we're not going beyond 9, because the units digit is any number from 0 to 9. So this becomes 3, 9. Again, because u must be greater than 7. The only number that's odd bigger than 7 is 9. The t value is the 3. And then finally, the last part, let's take a look at the number 4. The number 4 bigger than that is 8. Well, what number is bigger than 8? That's odd. It's 9. So this is 4, 9. I can actually stop here, because if I make t5 as my next example, and I can show you, but even though we would stop, if I made t5, then this would become 9. Are there any odd numbers bigger than 9 that could be units digit? Well, no. Units digit, again, if a number is a number like 27, what possible values can the units digit be? It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So because of that, we know that this can't be bigger than 9. So we know that it must be stopping at 4. Again, this can't be bigger than 9, because once this is bigger than 9, it bumps up to the next level. So this cannot exist, because you can't have 5, 10 here. So let's take a look at our possible solutions for this problem, which is intriguing. One of our numbers is 17, one is 19, 27, 29, 39, and 49. Those, it looks like, all of our answers. Well, we can check them all, really. Okay, we can check them all by just switching the digits. 71, 91, 72, 92, 93, 94. Well, the difference here is definitely more than 36. The difference here is more than 36, more than 36, more than 36, more than... These are all differences of more than 36. So all of these possible numbers work, but nothing else will. Anything else that ends in an odd number that's 2-digit will not work. Again, it cannot be 3 digits, it's 2 digits. So that's why we have to stop here when we get to the 9. We can't get any bigger than that. So our solution set, technically, are these quantities right here. Okay? Your homework from this section is from section 3.1. You're going to be looking at the written exercises and the problems.